and make sure that took. Yep. Okay, so we are recording. Hey, we're on to more about the study of what an atom is. And just so we're clear, in PHY211 modern physics, our discussion is pretty much limited to the simplest atom that exists, hydrogen. On Wednesday, we'll talk about how to apply what we're doing with hydrogen to helium, as long as it only has one electron. So we ionize one of the electrons away, or even lithium, where we take two electrons away. The best we can do with the Bohr model is single electron atoms. And again, we'll talk more about limitations on Wednesday. So the Bohr model here continues on with what Rutherford and his colleagues attempted to do with their experiment when they bashed alpha particles into a gold foil. And their whole goal was to figure out what was inside an atom, to probe what was going on, what does it look like in there. And their result in a sentence is that they found an atom is pretty much empty space. So that's it. And so now Bohr is trying to develop an improvement on that picture. And I'm just going to show you a slide. It's actually from Wednesday. It's a review slide from Wednesday's talk that we'll be doing. And let me share it with you. And I hope you're seeing it. Let me don't see the border. So let's try again. Stop share. Share. PowerPoint. Looks like that one. There it is. Got the right one this time. Okay, so there's the Bohr model. And it all comes from Bohr's assumption that angular momentum is quantized. And we came up with two conclusions about where the electron in a hydrogen atom might be located. Okay, and the first place is for the lowest energy electron that a hydrogen atom could possibly have. It's located at this place called a Bohr radius. And from the assumption of quantized angular momentum of this electron, you can figure out that the radius is about half of an angstrom, 0.5 times 10 to the minus 10th. And then the diameter of an atom, then the size of an atom, is about a full angstrom, about 10 to the minus 10th meters. But he went a little bit further than that. He said there are these other states the electron could be in. And my best analogy, what I mean by a state, is if you think about the standing wave on a string experiment we did, there was the simplest state the string vibrated in, and then there was the next harmonic up and the next harmonic up after that. And hopefully you can picture in your mind what a bowed string or a plucked string looks like in the fundamental mode, and then the first harmonic, and then the second harmonic. Bohr was postulating something similar to that for the energy mode, the steady state mode that the electron would be in. He didn't believe it was orbiting around the nucleus like a planet orbits around a sun, but it had that same character. And one of the things about modern physics is it makes no attempt to predict where the electron actually is. It only gives you a probability of where the electron might be. And that was a revolutionary idea, because for generations, physicists believed that physics was predictive, that if you knew something about a particle right now, particularly its velocity, its acceleration, maybe forces that would be acting on it, you can be very specific about where the particle would be in the future. And with modern physics, the domain of the very small or the very fast, just not so. Okay, so then I guess the next thing is where it could be where the electron could be located in higher energy states, these higher modes, like the higher harmonics for the wave on a string. That's a good analogy. Okay, it turned out that there is this number, this index, which we call the quantum number, the principal quantum number, given the name n, the symbol n. And if the first one was at a half of an angstrom, the next one would be when n is equal to 2. and that would be 4 times a half of an angstrom. Okay, and you could see that if you could get the electron into a real high energy state, like n equals 100, and I have no idea how you'd experimentally do that, but you'd have a pretty big atom, wouldn't you? You might even be able to see it if you can do that. So that was the first part that Bohr came up with. The second was what the actual value of the energy was when the electron was in each of these states. And at the end of the day, you know, for electrons in a hydrogen atom, that the total energy is minus 13.6 electron volts divided by the square of that index n, that principal quantum number. And so that energy level diagram that's off on the right there, that tells us about where the energy levels of the various electrons are. And notice they're not equally spaced. I guess that is one of the bottom lines. As you move up to infinity, they get for n, they get closer and closer together in energy. Okay, and the final thing, and I think this is what Bohr was actually trying to do, is he was trying to come up with a model of what's going on inside an atom that would explain Rydberg's results. And so he did that by looking at these energy states and deciding that if an electron transitioned from a higher state, and say in my diagram right there, from the 3 state to the n equals 2 state, there would be a difference in energy of the electron in those states. Okay. And that difference in energy was exactly the energy of the photon that was emitted. So you just take our energy equation for a photon that we've been using over and over and over again, and that is that the energy is equal to Planck's constant times the frequency, or Planck's constant times the speed of light over the wavelength. Okay. And if you know what this difference in energy is right here, because you have this equation to calculate it, okay, find the delta energy between those two, and you can immediately calculate either what the frequency or the wavelength of the emitted light is. I've got a simulation for that here in just a second that I'll show you. But the bottom line, when Bohr turned the crank on this, okay, and used, I favored this. I think I've told you, I just hate writing 1 over 4 pi epsilon 0, when instead I could just write Coulomb's constant. And so that's what I prefer. But you'll see a lot of those kind of things to represent Coulomb's constant over 2. I find it really hard to see the important things in the equation. So I kind of favor that. But if you then use this same idea and solve, look, there's 1 over the wavelength right there, right? Solve for that. And that's what the Rydberg equation had. Pay attention to those constants right there, and you get, oddly enough, because of that n squared right there, you get exactly Rydberg's result. And if you're careful with all the constants out front, you get exactly Rydberg's constant. Okay. And so that was pretty profound, that from a theory of what's going on with the energy levels inside a hydrogen atom, Rydberg's results for hydrogen could be reproduced. And just some things that we come to find: how fast should that electron be moving? We've got an expression for that. And then I talked about a constant that is not overly significant in modern physics, but you'll see it perhaps in quantum mechanics later on. It's a constant of nature, what the speed um, of that electron in the hydrogen atom is compared to the speed of light. It confirms we don't have to use special relativity for the thing. It's 1 over 1/37th. So it's the speed of the electron is over 100 times less than the speed of light. We're safe with classical energy expressions. Okay, here's my simulation. Any questions on anything I said right there? That's the stuff of today. And the worksheet problems, when we break up into groups, are gonna flow right from everything that's on this sheet right here. So this is kind of your equation sheet for this material. Questions? Nobody's saying anything in chat, so everybody looks like they're pretty happy. Here's the simulation, and it's that group up in Edmonton. Love those folks. They do some awesome simulations. This one isn't much, but if you're having trouble visualizing what I'm talking about, I found it a little useful. Let me share with you. Where is their stuff? Let's go right there. Okay. And you can see I'm going to do this atomic transition one right here. And are you seeing a photon coming in and hitting an atom? Somebody give me a thumbs up or something on that.
I can't see anything.
You're not seeing anything? Let me stop
Mm-mm.
sharing it then. And then we'll try sharing it again. There it is. Okay, I see a green border now. See,
Yeah.
the photon comes in when the electron, and all those green dots are where the electron could be, right? So the photon comes in, hits the electron, promotes it, we would say, up to the n=2 state. It hangs there for a second and then falls back down to the n=1 state. And notice the photon gets emitted when it falls back down. And so what we're showing are two things. I spoke mostly of Rydberg's equation because Rydberg talked about light being emitted from hydrogen gas in a tube excited with a very high voltage. But apparently the opposite is true, and mentioned that in a pre-lecture video. When it goes from 1 to 2, a photon is absorbed by the hydrogen atom. And so if you look at an atmospheric transmission spectrum coming from the sun, the exact wavelength or frequency that corresponds to hydrogen going from the 1 state to the 2 state, well, that's kind of a missing line. Okay, there's a color that isn't there because it's being absorbed by the hydrogen, which is in the water molecules, the water vapor, I should say, that's in our atmosphere absorbing. Okay, and so that's the picture we're showing. The green dots represent possible places where the electron could be. And I guess when n=1, we refer to that as the ground state, the lowest state. Oddly, we call the energy of that state E0, even though it's the n=1 state. And when it gets up to n=2, like it goes there for a second, that would be, we refer to that as the first excited state. And you can see the analog to harmonics of that oscillating string that I was talking about that we did in the lab in PHY211. Okay, and so there's a higher energy mode 2 right there, and then a lower energy mode. And when the electron drops back down, it gives off a photon whose energy is exactly equal to the difference in the energy of those two states. And then you can calculate what either its frequency or its wavelength is from energy is equal to Planck's constant times frequency, or Planck's constant times the speed of light over the wavelength. Pretty neat stuff. Okay. Anything else I want to say about that? No, I think that's probably it. And
I have
so
a question.
if there's no questions, anybody question? I thought I heard somebody talking.
I got a question.
Sure.
Yeah. So when we talked about when you talked about how we cannot predict where the electron is going to be at any point, is it something that as also with the circles that you showed, it's you would it could be anywhere honestly in that ring. So is it something that we are not learning in this semester that's true, or is this just not possible to predict?
Yeah, and we will be talking about something called the Heisenberg uncertainty principle. Remember Heisenberg from Breaking Bad, the name that he took? Well, that's who he's talking about, a famous physicist chemist. Heisenberg maintains it's just not possible to know both the position and the speed of an object at the same time. Okay, actually, he said momentum and position at the same time. So the best we can do, and we will talk about this before the end of the semester, is predict the statistical possibilities of where the electron might be. And of course, the shape of the curve is likely to have a maximum. And so you can even go to, hey, that's the most likely place where the electron could be, but it still is statistical. It's not necessarily there. It's like, the most probable grade, I guess it's called the mode, right? We can find that if 1,000 people took a physics test, there is the most probable grade, but there'll be many students who don't get that grade too, right? So there'll be many electrons in various hydrogen atoms that won't be at the most probable location. And so that's how it is. By the way, we call that position where the electron is most likely to be, we refer to as the expectation value of the electron's position. And that's stuff that we'll be talking about in more detail. You'll love the math of that because in order to solve for that that most probable position, we have to do a little bit of differential equations, which I think most of you have not had. Most of you will be taking differential equations, if I understand it, next semester. And so we'll be giving you an introduction and a quick overview of how to solve differential equations in order to get that. To answer your question, so no, we don't think it's just a limitation on our class or any other class that you or a graduate student in physics might take. We actually think this is a limitation of nature. Nature just doesn't reveal it. The fundamental physics properties of things that are very small to our knowledge right now does not reveal itself to be predictive in position, velocity, future position, future velocities, accelerations. We don't do that. All we can do is figure out where things probably are and do a statistical understanding of where the electron might be.
Thank you. Yeah, that solves it.
Yeah, no, that was the book. If you take quantum mechanics class, the guy who actually put that in my head, I was in graduate school before somebody gave me that, was the author of that, the physics book you'll use. Oh, I've forgotten his name already. Griffiths. His name is Griffiths. He teaches at Reed College in, I think, Washington State, somewhere in the Northwest. Maybe it's Oregon. In any event, he came and gave a talk I listened to, and he said, hey, that's the fundamental difference between classical physics, like we learned in PHY 111 and 112, and the modern physics, the quantum physics that you're going to move on. Classical physics is at its very core predictive. If you know enough about an object right now, you can look into the future. That's how we got to the moon, right? That's how maybe we'll get to Mars someday. We can predict what's going to happen in the future based on what we know right now. The domain of the very small, the subatomic world, just doesn't follow those rules, or at least doesn't reveal itself to us. And by the way, one of the things you notice about the Bohr model is when the electron goes from either that n=2 to n=1 state, where it gets demoted and gives off a photon, or when it absorbs a photon, goes from the 1 to the 2 state, we don't know anything about the physics of that transition. We believe it happens virtually instantaneously, and we don't know why, and we don't know how. It's, those are one of the limits of what our knowledge is. And we just accept the fact that it happens and that the rules of classical physics aren't involved. And, when people like Bohr start saying things like this around the time of World War I, people think they're crazy. I mean, they have to, part of the reason why I think Bohr has to stay close to a planetary model in this theory that he proposes is because he didn't want people to think he was so extreme in his physics views that his views would be completely discounted. And so that's some of what we got here. All right, probably more than we need to say on all that. Let me shift over from that model, ending it.